Okay, what I like to do now is introduce the second limit definition of the slope of the slope of the tangent line from the limit of a secant line. So, I'm going to start off just like we did last time. We're looking at this function, and we know as the second point gets closer and closer to the first point, the slope of the secant line gets closer and closer to the tangent line. So, I'm going to take a quick screenshot of this and begin our process. Now, the only thing I'm going to do this time is introduce the change in x, and that is my change in x we know is x minus a. Now, I'm going to introduce a new symbol for that, and we're going to call this distance h. It just represents the distance in the x direction. So, here's our little rectangle, our rise and our run. And our run has a distance of h. And I'm going to leave the rise just as it was, but actually I'm going to change the rise just a little bit. So, the second value, the second x value, the second y value is, of course, f of x. But also, to get from a to x, we know that you're basically adding h units. In other words, I start at a and add h units to get to the second x value. So that has to equal this that I'm labeling as x. So I can rewrite f of x as f of a plus h, because a plus h is x. Now, why do I do that? Because I'm going to set my limit up a little bit differently. So the slope of my secant line is the second y value, which we've now renamed a little bit, minus the first y value over the run, which is the distance from the first x value to the second x value, which we've already said is h. So this is just another way, using some slightly different symbols, to represent the slope of the secant line. And of course, once again, I want the slope of the tangent line. Let me change colors. That's my purple line. So the slope of the tangent line is going to be that limit as that distance gets smaller between the second point and the first point, but that distance, we said, is h. So as h gets smaller, which means approaches 0, the 2 points are coming closer and closer to each other. And this is my second limit definition of a slope of a tangent line from the secant line. Now let's apply this to a problem. Let's say I'm looking at an equation of a function. Oops. Hang on just a second. So I'm looking at the equation of a function y equals 2 over x. And what I'd like to do is, hang on, I'm just going to make this go up so I can have some more writing room, is find the equation of the tangent line at, let's back that up. And let's let x equal 2. So if I plug in 2, 2 divided by 2 is 1. So there's a point, and that is a point on this function, and I'd like to find both the slope of that tangent line as well as the equation of that tangent line. So we're going to apply our theorem. So the slope of that tangent line equals the limit as h approaches 0 of f of a plus h, and a is 2, minus f of a over h. But now I'm going to actually calculate the f of 2 plus h and the f of 2 using my function as it was given to you right here. So the slope of the tangent is going to equal the limit as h approaches 0, f of 2 plus h. I'm literally going to plug in 2 plus h using a substitution for my x, minus f of 2 all over, oops, sorry about that. Calculator's getting a little bit glitchy on me. All over h, which is just going to stay h. Okay. To make this happen, I need to simplify this. So I'm going to combine these two fractions together by simplifying. So I have 2 over 2 plus h minus, that's the h there, sorry. 2 plus h minus 1 over h. And just over to the side, I'm going to examine 2 over 2 plus h minus 1, and I'm going to convert that 1 into a fraction that has the same denominator as 2 plus h. And I'm going to do that by taking the top and the bottom and multiplying by my lowest common denominator. So now I've got the 2 over 2 plus h minus 2 minus h all over 2 plus h. So when I simplify this, I end up with 2 minus 2 minus h all over 2 plus h, or simply negative h over 2 plus h. Please don't forget what we were doing. We were only attacking, I'm sorry about that, the numerator. That's all. So we have simplified the numerator, and now I'm going to put in that new numerator. And again, this is the slope of my tangent line. So my slope of the tangent line is now the limit as h approaches 0. I still have h in the bottom, but now my top, it becomes negative h over 2 plus h. So I have a rational function, and I have a denominator over a denominator. I'm sorry, a fraction divided by a number. So instead of taking a fraction and dividing it by something, I'm going to redefine that using my properties of fractions and say I do not take a fraction and divide it by something. I take that fraction and I multiply it by the reciprocal instead. That's an h. So again, simple property of fractions. this reduces h on top, h on bottom, leaving me a negative 1 all over 2 plus h. And what's nice about what I have here on this limit is I've got a rational function, and on the top it's a constant, and on the bottom it could be considered a polynomial. And polynomials allow direct substitution, and a rational function also allows direct substitution when it's polynomials if the bottom does not equal 0. In this case, the bottom does not equal 0 when I plug in h equals 0, and I end up with negative 1 over 2 plus 0, which is simply negative 1/2. So now I have the slope of my tangent line using the second definition of the limit of a secant line. So I'm going to go back up. Oops. Let's make it small. And let's remember, I had a point, 2, 1, and now I have a slope. So my point is 2, 1 with a slope of negative 1/2. That is all you need to come up with an equation of a tangent line. Make it a little bit bigger. The equation of a tangent line in point slope form is y equals slope times x minus the point on the function, x value, plus the y value of the point on the function. So this is the equation of my tangent line in point slope form. If I want to simplify it and put it in slope intercept, that's fine. So point slope and slope intercept. Both of these equations are valid equations of the tangent line to my function to the given point.